Hi, welcome back. This is the third session on product topology and Tyknoff's theorem. In all possibility, I will state and prove Tyknoff's theorem. Okay, and it depends how much I want to go back and forth. Okay, let us see. And yeah, I should warn you, I am not going to review partial order Zorn's lemma. You can see that in one of my videos, partial order and Zorn's lemma, and also in Harmonic theorem. I think the third session I had completely reviewed again Zorn's lemma. But if I do that, I may not be able to complete the proof. So please go through it. And second thing I am assuming is that you have gone through the first two videos so that you become comfortable with the notation and also you understand what is product topology and what are the basic open sets in product topology. Okay, they are very important. I'm not going to review. Okay. With this preliminaries, let us get started. Yeah. Before we start, just one thing. Yeah, this is my channel and this is my email ID. Please, when you want to refer to something to do with the videos, please write to this email, not to the other email. Some of you are sending to that. Please don't do that. Yeah. And one thing is the list of videos. Okay, it gives the descriptions, links of the videos, and the videos are arranged in the preferred order of viewing within the topic. If it's topology and within topology, continuity, like that. Okay, compactness, etc. So they are periodically updated. In fact, one of you has volunteered to look after this list of videos. I'm very really thankful to that guy. That is Mr. Amit Mittal. Okay, let's get started. Okay, so what is Tychonoff's theorem? So let us talk about xi. I is an indexing set. These are all topological spaces. Okay, we define what is meant by Cartesian product xi in I. Okay, and the product topology whose has basis the elements of the form. Okay, phi I inverse of ui, I running from a finite set A. A is a subset of I which is finite, and ui's are all open in the thing xi. These are xi tau I. Okay, these are all open. This is the basic elements. Okay, this is all you will need to go through the proof. Okay, right. So let us what the theorem, Tychonoff's theorem says the following. Assume that xi tau I is compact for each I in I, then x equal to product xi I in I is compact with product topology. Tau p. This is the topology whose bases are these elements. Remember, these are all the pi a inverse of ui. If you had looked at my first lecture on this, you will know how to look at these things. And you also know what does it mean by I intersection over a pi a inverse of ui, how it looks like. You have a geometric description. Okay, it's not just simply set theoretic thing. We had explained all these things. Now, what is the plan? The plan is very simple. Let x be any set. Okay, and yeah, the plan is we will invoke. Okay, we shall prove this by using finite intersection property of closed sets. So let us recall what it says. So we say X is compact if and only if okay, every family of closed sets with finite intersection property. Let me say F. Okay, intersection property has non-empty intersection. let us say what it means. I have a family F, right? So let us look at F in capital F. Remember, each of these element F here is closed. And what do I know? If I take finitely many elements F1, F2, Fn, their intersection is non-empty. This is given. Then that means the intersection over entire family is not empty. Okay. Again, I am not going to give this proof because this has been seen in compact things. So this is well known. It's also easy to prove. Okay. So this is what we want to prove. Okay. So what we are going to do is first a set theoretic observations. First, suppose X is any set. Okay. And F naught be a family of, okay, with a finite intersection property. Notice that this is just any set, therefore nothing to do with closed or anything. Okay, a family of subsets and it has finite intersection property. Then first thing is there exists F which is contained in P of X with the two properties such that one, F naught is contained in F, and two, F has FIP, and three, F is maximal with respect to properties 1 and 2. 1 and 2. What does that mean? So these are the things you have to be careful. That's why I sincerely request you to go back to my partial order and Zahn's lemma. Become very comfortable. I know 90% of the students, master's students, are not very comfortable with Zahn's lemma. Okay, please go through it. You will become very comfortable. So what does this mean? First, it says there exists one. This is a clear. F naught should be contained in this, and F also has a finite intersection property. That's also clear. What does this mean? This means if suppose G is also contained in P of X and said that F naught is contained in G and G also has FIP, then and if G contains script F, that implies G equal to F. This is what maximality means. Okay, maximality means the following. Suppose you find some other family G of subsets which contains F naught and G also has finite intersection property and G contains F, then G has to be F. Okay, that I say F is maximal. Okay, now we want to prove such a thing exists. Okay, so how do I prove that? Okay, let me just denote, since I will be running out of notation, let me write this F to be set of false families F such that, okay, F contains F naught and F has FIP. Okay, so this is non-empty. Why? Because my F naught itself belongs to this. Okay, you notice that this is a strange double F notation, like a field notation, consists of all families of subsets. Okay, this is a much bigger thing. Okay, now given F and G, I want to put a partial order on this. Okay, what is the partial order? If you give me F and G and this, I say F is less than or equal to G if and only if. Remember, if you had looked at, watch my video on partial orders and John's lemma, you would see the single most important partial order set theoretic inclusion. Okay, in mathematics that's very often used, so learn that. Okay, this is the thing. Okay, this is a partial order. I am not going to check. Okay, check, this is a partial order which is very easy. Okay, right. Now what do I want to do? I want to apply Zahn's lemma to this because I want to find a maximal element. Okay, so how do I do that? For that I have to make sure F has some property. What property? If, let us say, T, okay, I don't know, okay, T is a totally ordered family for all, let's say, subset of this. What does that mean? This means Monkrus calls this chain. What does it mean is this tau is a collection in this. Okay. What is this tau? Remember again, it consists of all such families f of subsets, okay, of x, so that f contains f naught and f also has finite intersection property. So I have a collection. So this is totally ordered. What does that mean? Give me two elements f1, f2 here, then either f1 is less than or equal to f2 or f2 is less than or equal to f1. That's what is meant by saying it's a totally ordered or it's a chain. Then what I have to prove? I have to prove this T has an upper bound. Where? In my family W. Okay. What does that mean? That means there exists some, let us call it G in script f, so that for every f in tau, okay, f is less than or equal to G. Notice that the G may not be in tau, but what I want to say, it is in the given family. Again, if you had watched my videos on Zorn's lemma partial order, you know how to find an upper bound. So okay, let us define G to be union of f and f in this. Okay, this is where you have problems. Okay, not only we are talking about sets, subsets, and family of subsets and family of such families of subsets. Okay, notice that I have x. Okay, then I have family of subsets, and then what do I have? I have family of subsets of x. Okay, so it's a good to watch my video so that you become more and more comfortable. All of a sudden, if you this is the first time you are seeing this, you will get confused. Okay, right. Anyway, so this is union. This is all right. I first notice that. Okay, what is that I have to prove? First, notice that given any f and tau, then f is contained in G. This is clear because it's an element of this, right? Okay, therefore it's contained in this. That's correct. Okay, and also f naught is contained in G. Why? Because f naught is contained in each and every f, therefore it's contained in G. That's also clear. Right? Then I want to say it's an upper bound. That is again clear. Okay, this shows f is less than or equal to G. Right? The only thing I have to show is if I want to show G belong to my family tau, okay, so I have proved f naught is contained in G. Okay, I have to prove G has f by p. Okay, pause, review, proceed. Okay, that is very easy because suppose f1, okay, you give me elements, okay, you give me elements a1, a2, an and g. What I have to show? A1 intersection to an is not empty. I have to show this. What is G? Remember again, G is union of F. What is F? F is family of some family of subsets of X. Therefore, G is a family of subsets of X. Okay, keep that in mind. Okay, these are the things people get, you have to get used to it. Okay, G is a family of subsets of X. So when I want to say G as FIP, what do I mean? I have A1, A2, AN and G. What are A1, A2, AN? They are subsets of X. I have to show that their intersection is non-empty. How do I do that? Since AI belongs to G, there exists an Fi in that. Okay, what is G? G is the union of these elements. Therefore, there is one Fi here in tau, such that my A belongs to that Fi. You understand that? Such that A belongs to Fi. Okay. Now let us look at this family F1, F2, Fn. Okay, this is a finite family. Contained in T. This is a chain. Okay, therefore there exists a maximum in this, namely say Fk. What does that mean? All Fi is less than equal to Fk for 1 less than equal to k. Right? Whenever I have finite number in a totally ordered set, okay, it has a maximum. Okay, please, okay, how many times I can tell you? Please watch video on partial order and Zorn's lemma. Okay, let's come back. Right, therefore, since A belong to Fi and Fi is contained in Fk, therefore A1, A2, Ak, where are they? They are in Fk. You understand? But what do I know about Fk? Fk is in tau. But where is this? Okay, this is a subset of my capital F. And therefore this is Fk is an element of this F. Okay, but what do I know? Every element here has FIP. Right? Therefore A1, A2, An are in Fk. Therefore Fk has FIP. Therefore A1 intersection An is not empty. So what I was shown? I have shown that, okay, this G, this family tau has an upper bound in F. Okay. So by Zorn's lemma, what does Zorn's lemma says? Zorn's lemma says if X is a partially ordered set, okay, so that every totally ordered subset X, that is a chain, has an upper bound, then X has a maximal element. This is what Zorn's lemma says. Okay. Now, so I am going to apply Zorn's lemma to where? To this F. This is a partially ordered set. Okay. And what I proved? Every chain has an upper bound. Therefore, by Zorn's lemma, there exists script F in this, which is a maximal element. Right? So, what kind of F this is? This F belongs to script F. This F, that means F naught is contained in F, and F has FIP, and F is maximal. Okay, what is the meaning of maximal? I already said that. If G also belong to this, okay, and F is contained in G, that implies F equal to G. Okay, this is what maximality means. See that how many times I keep repeating. Okay, this is what you have to learn. PRP. So let us go back and try to understand. So what I have shown now, okay, a set theoretic observation is what we did. If I have any set X, if I have a family of F naught, which is a collection of subsets of X, and what the property of F naught is, it has finite intersection property, right? Okay. What does it mean to say finite intersection property? Remember, F naught is a class of subsets of X. Therefore, if you have some A1, A, An, and F naught, it is same as saying A1, A, A naught are subsets of X. So, when I say it has finite intersection property, what does it mean? A1 intersection A2 intersection An is non-empty. If that be the case, okay, by Zorn's lemma, what we proved was there exists a family F, okay, which is a subset of Px, that is family of subsets of X, with what property? 1, F naught is contained in F, and 2, this F also has finite intersection property, we have enlarged it. And still, and third property is very important, F is maximal. What does it mean to say maximal with respect to these two properties? If G is also a family of subsets, such that F naught is contained in G, and G has FIP, and F is contained in G, then F has to be G. Okay, that's maximum. Nothing can be bigger than that. Okay. So take some time, understand. Okay, right. So now next observation is this. Okay, suppose F again is just a set. Okay, X is a set. Okay, has FIP and maximal. That is, if G is any subset in P of X and F is contained in G and G has FIP, okay, that implies F equal to G. Okay, I'm just repeating so that you get used to that, because students have problem with maximality and thing. Okay, then then if A is a subset of X, so that A intersection F is not empty for every F in script F, then A itself is in script F. Do you understand this? Try to understand. Do not. So let me remake it observation 2. Okay. So what do I have? I have a family of subsets with a finite intersection property, and this family of subsets is maximal. What does it mean? If G is another family of subsets, G also has FIP, and if F is contained in G, then F and G are the same. Okay. If I'm given such an F, and if you also give me there is a subset A of X, so that A intersects each and every F non-trivially, that is A intersection F is non-empty for every F in the family of subsets, then A itself has to lie there. This is a very trivial observation. Okay, this proof is very easy. Why? Okay, consider G equal to F unions only this singleton A. Remember, this is class of subsets, so I am adding one more subset. Alright, now this contains script F. Okay, is that clear? Right. Next, I say G has FIP. Why? There are two things. Suppose you give me B1, B2, Bn in G, right? Or if you call G1, G2, Gn. G. If all my things G1 to Gn are in F, then the G1 intersection Gn is non-empty. Right? If. Okay. Otherwise, what will happen? One element may be A. Maybe many more elements, but at least there is one element A. Is that clear? Right? So, suppose my G1 is A. Okay. I do not know anything about G to Gn. Okay. Or if you want, collect them in such a way so that G1 to Gk equal to A and Gj are in F if j is greater than or equal to k plus 1. Okay, because G1 to Gtn may have many elements, right? Right. Okay. Now what do I know? Okay. I have to say this is non-empty. Okay. How do I do that? So let us look at A. Okay. Okay. G1 intersection Gn is okay A intersection Gk plus 1 intersection Gn. Right. Now I know this intersection this is non-empty, this intersection this is non-empty, but I do not know whether this intersection this is non-empty. This is what I want to know. Suppose I know okay, sorry, F1, now they are all, let me call them as F1, F2, Fn. Okay. So what I want is A intersection something like Fk plus 1 intersection Fn. So let me just simply say some F1 intersection Fn. Right. My family G1 to Gn is nothing other than this. Okay. Right. So if I know this also in F, then I am through, because A, suppose this is an element of F and A intersects every element of F non-trivially, therefore this will be non-empty. You understand this? Yeah. So this will follow if we can prove for every F1, F2, Fn finite family in script F, F1 intersection Fn is in script F. We know it is non-empty, but I want it to be an element of F itself. I want to claim that. Suppose I have proved, okay, then go back. So you gave me G1 to Gn, okay. some elements may be A, take them out, and after that whatever elements are there, they are in elements of script F. Okay, therefore I can write them this intersection G1 into Gn as something like A intersection F1 F2 Fm something, right? Now F1 to Fm, where are they? They are in F. Okay, if I show that this intersection itself is in F, so by the property of A intersecting every element of F, this intersection will be non-empty. Do you follow that? Okay, right? Okay, so if this intersection is non-empty, then what happens? Okay, this G has FIP and G contains F, therefore by maximality of F has to be G. That is same as saying A belongs to F. Do you understand this proof? So what remains to be shown? We have to show only this point. Okay, pause, review, proceed. Okay, so let okay F1 Fn be in script F, and F is what? FIP and maximal. Okay, keep that in mind. So let B equal to F1 intersection Fn, right? Now look at F, look at G. This is not the same G as earlier, okay? Maybe I will call it H equal to script of union B. And this contains script of? Yes? Okay. Right? Then H has FIP. That is very clear because you start with any element F1, not this F1, some A1, A2, AM in F. Okay. As earlier, I can take B intersection A1 intersection AM. Right? But you follow that? I want to prove this as non-finite intersection property. Therefore, I am going to give some elements of this. So, as I said earlier, if all elements are in script F, there is nothing to prove. Therefore, let us assume there is one element, one element, namely B, which is not in F. Then B intersection some finite number of elements in EM, right? But what is B? B is F1 intersection Fn, and this is A1 intersection AM. This is equal to this. But where are these? All these elements are in script F. So what do I know about script F? It has FIP. Therefore, this is not empty. Therefore, this shows this is not empty. You follow that? Okay. Therefore, what is the conclusion? So this has FIP but contains F. Thereby maximality. Okay. H has to be F. That means B is in F. But what is B? B is arbitrary finite intersection of elements coming from F. Okay. Pause, review, proceed. So in summary, let me put it in a slightly different way. X is a set, F is a FIP family with the maximality. Okay, then what did I do? The first thing is I will prove the second one. If A1, A2, AN are in F, then A1 intersection A2 intersection AN is in F. And 2, if B is a subset of X such that B intersection F is not empty for all F in script F, then B is in F. Okay, this I made as 1, this as 2, now I am changing. Okay, please make sure this is what we did. Okay, A1 intersection AM, this is not empty. How did I prove that? Quickly go through the proof. You call this as script A, then look at F union script A, and you say this as FIP. And maximality imply that. And similar reason here. Okay, script of union B. Okay, idea is very simple. The only thing is you have to review. Okay, it's pure set theory. There is nothing. Okay, very deep anything. Okay, please pause, review, proceed. So you saw what was required as theorem and set theoretic thing, okay, many students get confused because, as I said, you start with the set and you start with the family of subsets and then family of such families. Okay, so every time you should spend some time, don't simply assume, become familiar with that. Okay, then you will feel comfortable. Okay, please go through this. Okay, after few minutes break, I will, because already the time is about 31 minute. Okay, and that will again require about 40 minutes or so, the Tychonoff's theorem. So I think it may be a better idea to prove it as a second thing, or I will, after a few minutes, I will again prove it and merge both the videos together. But if it's a single video, my sincere request is stop here and review from the beginning all the set theoretic things, okay, before launching into the proof of Tychonoff's theorem. Okay, let us stop. I'll continue again. Okay, I hope you reviewed whatever happened so far about set theoretic thing, and hereafter Zahn's lemma will not appear. Okay, now we will go to the proof of Tychonoff's theorem. Okay, what is the basic idea? I will just give the basic idea, and if necessary we will also summarize at the end of the proof. Basic idea is very simple. Suppose I have a family of closed sets with finite intersection property, call it script f, okay, which is sub, okay, family of subsets of x. What is x? X is product of xi, and each element of script f is closed. It has finite intersection property. Very good. So now forget set the topology, etc. So script f is a family of subsets with FIP containing P of x. Therefore, by the set theoretic lemma, okay, call it F naught. Okay, call it F naught. So by set theoretic lemma, we know there exists a maximal element script f, okay, which contains F naught, and script f has finite intersection property. Notice that script f is a collection of subsets of x, where x is product of xi. So script f need not, the elements of script f need not be closed at all. But what do I know is it has a finite intersection property, right? So intuitively, okay, what we want to do, we want to choose, okay, take this script f, which is a maximal family, project it on the xi, the ith factor, right? Then I will get, it will have a finite intersection property, okay. Then take the closures of elements. Okay, maybe I should, you may get confused. Let us just write and then do that. Okay, even, yeah. So we are going back to our assumption x, which is product of xi, and xi tau I are compact. Okay, then we want to show. So let this be, okay, family of family of closed sets with f. Okay, the family has FIP. Okay, what do we have to prove? We want to prove there exists an x in f has f in f naught. You have to prove this. Okay, then we know then x is compact. Okay, this we had already seen this, a well known result. Okay, the basic idea is this: by set theoretic lemma we know that, okay, this f naught is contained in f. Okay, f is a power set of x. Okay, and if f belongs to this, does not imply f is closed. Okay, it's only some class of subsets, but this script S has FIP and it's maximal. Is that okay? Now let us look at pi I of script f. This is pi I of f as f here is so this. Okay, this is a family of subsets of xi. Okay, it's very easy to see this as FIP. Okay, if this is FIP, then let me look at phi of f closure. This set of all pi I of f closure f and script f. This again, okay. Notice that these are all closed subsets. Okay, p of xi. But these are all closed sets, and we know xi is compact. Therefore this intersection, okay, of whatever you call it E in pi a of f closure, okay, E, this is non-empty. So therefore there is an element. Okay, remember all these elements are in xi. Okay, they are all closed sets. Okay, now look at x equal to xi. Okay, this is an element of product xi. I want to say x belong to intersection of f as f where is over f. That's it. Okay, this is what we want to claim. Okay, that means it's same as saying x is an adherent point of f for every f in script f. Right, x belong to f closure simply means x belong to f closure if only if x is an adherent point of f. Right, therefore this is all we want to prove. Suppose I prove that, remember, if f is in f naught, then f is same as f closure. Therefore what I have is, okay, f in f naught contains this f closure and f in script f. Right, this is same as f closure. You understand? Okay, but this is not empty. That means this is not empty. Therefore I have proved the result. This is the basic idea of the proof. Please stop. Okay, pause, review, proceed. This is a strategy. Okay, let us get started. So f naught is a family of closed sets in X, and this family has FIP. Okay, so by set theoretic lemma, we know observation 1, we know there exists f containing f naught and f as FIP. Notice that script f is a family of subsets of p of x, and elements of script f need not be closed. Okay, right. The first observation I want to do is we define a collection pi of f. This is by definition pi a of f as f is script f. So this is a collection of subsets of p of xi. Do you understand that? I want to claim this as FIP. Okay, this need not be again closed, need not be closed. Why? Projection map is open, but the projection map need not be closed. Okay, but remember f elements of script f need not even be closed. Therefore there is no way of saying pi a for closed sets. But as class of subsets of xi, we want to say it as FIP. Why? That is very clear. So start with some element e1, e2, en in pi a of f. I want to prove e1 intersection en is not empty. Right? But notice that there exists f1, f2, fn in script f such that pi a of fi, sorry, phi a of fk is ek. 1 less than or equal to k less than or equal to n. Right? Now, where are f1, f2, fn? They are in script f. And script f has FIP. Therefore, what do I know? There exists a z which belongs to f1 intersection fn, because this is not empty. Right? Now let's look at zi equal to pi a of z. Okay. Therefore z belongs to fi for all fk, let me see. Okay. For 1 less than or equal to k less than or equal to n, this implies pi a of z belong to pi a of fk, but that is ek. That means my zi, call this zi belong to E1 intersection En. Okay, so pi I of f has FIP. Okay, pause, review, proceed. Yeah, now let's look at this is a very simple observation. Suppose if a family I in I, this has nothing to do with this I, okay, some indexing set. A alpha, alpha varies over lambda, okay. This has FIP, and if you assume A alphas are contained in B alpha for each alpha, and this B alpha, alpha and lambda has FIP. You see that how many set theoretic observation we need? Huh? Did I share the screen? Yeah, sure. Okay, that is very clear. Yeah, if you take something like B1 to Bn, okay, then A1 to An is contained in this, and this is not empty. Therefore, this is non-empty. Okay, is this clear? Therefore, what I want to say is, let us look at pi I of f closure as f varies over f. This I will simply denote it by pi I of f closure. Okay, this is just a notation. Okay, remember pi I of f, this family has FIP, right? Therefore, this family pi I of f closure contains pi I of f. Therefore, by this observation, this is FIP. Okay, but what do I know about pi I of f? These are all closed sets in Xi. And what do I know about Xi? Xi is compact. Therefore, there exists an Xi which is common to pi I of f closure as f varies over script f. So I found. So pause, review, proceed. So now I find an element product Xi such that x at I is my Xi. Okay, I define an element. Okay, now what you want to prove? You want to prove x belongs to, this is what I said in the strategy. Okay, f closure f varies over script f, which is same as saying x is an adherent point of f for every f in script f. Okay, if I prove that, as I said earlier, this is contained in f1, f naught, because if f is in f naught, f closure is same as f. Therefore, this will be every element here will be an element here. Therefore, this intersection is non-empty. Therefore, this is a bigger set. Therefore, this intersection is non-empty. Okay. So we would have concluded X is compact. Okay. I'm just repeating the strategy again so that you get confirmed. Okay. Confidence in what we want to do. Now, to prove this X is an adherent point and point of f for every f in script f, what I have to do? You start with any basic open set, okay, pi, let us say, intersection pi I inverse of ui, I varying over a finite set. A is a finite subset of I. And what are ui? Ui's are open in xi. And what is here? My xi must be open neighborhood of ui, right? So this is a basic open neighborhood of x. So what do you want to prove? So we want to prove, since x is an adherent point, so we have to prove intersection I in A of pi I inverse of ui, this set intersect with f is non-empty for every f in script f. Therefore, every basic open neighborhood of X intersects F. What is F? F is an arbitrary element of script, the family F. Therefore, I would have proved X is an adherent point of capital F. Is that clear point? Okay. Okay. So, pause, review, proceed. So, how do I prove that? So, first thing is, we will first prove my, with the same notation, that is ui belong to tau I and xi belong to this in open set, then I will prove this itself is belong to script F. Okay. Now, what is the advantage of this? How many of you see that? If this belongs to script F, this has FIP. Therefore, if you give me any F in script F, then pi I inverse of ui intersection F will be non-empty. You understand? So, if I prove this, it implies this. Because script F has an FIP, this is an element of script F, family F, this F is an element, therefore this is intersection non-empty. Right? Okay. Now, how do I prove that? Okay. Now, let us look at xi. Xi belong to ui, right? And xi belong to pi I of f closure. Remember what was my xi? Xi is intersection of pi I of f closure as f is a script f. Therefore, xi is an adherent point of pi I of f. It belongs to the closure, therefore it has been an adherent point. So, what does that mean? That means ui intersection pi I of f is not empty. Is that clear? Yeah, it's an adherent point. But if it is not, therefore there exists a zi which is here. Right? Now zi is where? Zi is in ui and zi is also in pi I of f. What does that mean? That means there exists z in f so that zi is pi I of z. Right? Now, is it clear? Now I claim z belong to pi I inverse of ui intersection f. So, claim. Okay. Why does that follow? It follows because z belongs to this if and only if. What happens? Pi of z must be in ui, which is zi. That is clear. And z must be in f. That was by choice. Therefore, this is correct. Yeah. Therefore, what I have concluded? So, pi I inverse of ui intersection f is not empty for every f. But f is maximal. Right? F is maximal. Therefore, by observation 3, I do remember second and third observation interchange. Therefore, this is the observation 3. Okay, it pi I inverse of ui belong to script f. This is a theoretic observation. Whenever a maximal family, if A intersects each and every element of the maximal family, then that element A itself is in script f. Okay, just try to think like that. Okay, is it okay? So pause, review, proceed. Now choose any finite subset A of I and choose open sets ui in tau I so that my xi, remember my xi's are all fixed, they are not variable now, right? Okay, right, this xi belong to ui, right? Okay, now what do I know about pi A inverse of ui? These are all in, these are all in script f for 1 less than or equal to I less than or equal to whatever in, if A modulus A is in. Okay, simply for all I in A, that's good enough. Yeah, is that okay? Right? Now these are all elements. Now start with any element f in script f, then by f as FIP. Therefore, what do I have? Pi I inverse of ui intersection I varies over A. This along with f, this is not empty because all these elements are finite number of elements in script F, and script F has FIP. Therefore, what do I have? This is non-empty. Is it okay? Right. But what do I know then? Pi I inverse of ui intersection I over here, this any arbitrary basic open set, open neighborhood of x. So it intersects F, and F is any arbitrary element of script F. Therefore, what does it mean? Z is, not x is an adherent point. Adherent point of F, that is x belong to F closure. This is true for every F in script F. Therefore, x belong to F closure, F in script F, but this is contained in script F, F in F naught. Therefore, the family is F naught, F family closed set has a finite intersection property, but the entire intersection is non-empty. Therefore, by the well-known result, okay, my X is compact. Pause, review, proceed. See the proof? It's a pure set theory, and if you learn very well, that's why I spent a lot of time in the Cartesian product in the first session. And for product topology also I spent time. What are the basic open sets, how to deal with them. Okay. And the third thing, and remember the third thing again, you will have problem if your knowledge about John's lemma is bad. So go back to my request. If you are not very confident, please watch my video on partial order, especially on John's lemma. All these things will be done with a little more detail, so that you will understand. When you come back, you will follow. It's a very beautiful proof. This is the simplest proof possible, and in fact, okay, at any time I find it easy without checking preparation. I can give the proof. Basic idea is very simple. The basic idea is the first set theoretic observation. What was the set theoretic observation? If script F naught is a family of subsets with FIP, there exists script F which contains F naught, which is maximal with FIP. Right? As a corollary, we made another two observations. One is all finite intersections of such family script F will again be in script F, and if A is any element of X, any subset of X which intersect each and every F in the family F, then A itself in the family F. Okay. After that, what did we do? We started with the family of closed sets with FIP in the product topology, right? And then we extend it, call it F naught, we extend it to F by set theory. Then what did we show? We showed that project F onto the ith factor, okay, take the closures of each and every element, then xi is compact, therefore there is a common element xi in intersection pi I of F, where F here is our script F, family F. Then I have an element x of the product space, x equal to xi. Then I want to show x is an adherent point of each and every F in family F. How did I show that? The observation is simple. That means if I take an arbitrary basic open neighborhood of x, it should intersect each and every F, because I have to prove x is an adherent point. How did I prove that? First observation was I proved pi I inverse of ui itself in the family F, and hence finite intersection of such elements are also in F. Therefore, it has to intersect each and every F. Element F of family F. Okay, there are too many words, right? If you have been following at least 20 or 30 of my lectures, you will find you can follow me. You will understand the mathematics also. Okay, right. Otherwise, you go back and again watch it. I am sure you will find it easy. And if you want, you can download that article from the website. So go through it. It will also help you. The notation may be slightly different, but once you understand the concepts, okay, you can set your own notation and prove them. Okay. I hope you enjoyed it. Okay. Right. So we will meet again on some other occasion.